All right, welcome everyone. We're going to get started. Can I get a quick check in the back? Can you hear me? Okay, awesome. So my name is Edward Oakes, and today I'll be telling you about RayServe. We've had a number of talks about RayServe throughout the day. This one is really going to be a high-level talk where I'm going to tell you about, where we are in Ray 2.0 and where we're headed in the future. So Simon Moe is also a co-author on this talk. He gave the virtual version, but it'll just be me here today. So a quick outline before I get started. So I'm going to start by giving you an overview of the motivation for RayServe, and then I'm going to go into a few highlights that we're really excited to announce for Ray 2.0 on some of the progress that we've made that is now available with the new release. So let's dive into the overview. So you've probably heard about Ray AI Runtime, or AIR, throughout the day. So RayServe is part of AIR, and AIR is really just a collection of libraries that offer basically a unified API and runtime for building end-to-end machine learning applications. So RayServe is, like I said, part of AIR, and today we're going to focus on the online inference, or going to production and really building APIs that are powered by machine learning models. So RayServe is flexible, scalable, and efficient compute for online inference. It's built on top of Ray, which means that we inherit a lot of the benefits out of the box that Ray provides. So we inherit scalability, low latency communication and response times, and also efficiency, which is really important when serving machine learning models. One of the key highlights that we really focus on in RayServe is multi-model inference, or model composition. And we'll dive more into that later. And RayServe is also Python native. So this means that you can easily mix business logic and machine learning, and you can use all of your favorite tools and libraries to build online inference APIs. So let's dive a little bit more into an example of a multi-model inference application. So for the rest of this section, we're going to use this working example of building a content understanding API. So you can imagine a user passes in an image. We pass it through some kind of machine learning process, and then as output, we want to have some kind of structured information about the image that's powered by machine learning. So in this case, we might do some object detection and say, oh, there's a hummingbird in this picture. We might have a confidence score that can be used to make decisions based on how confident we are about the object. And then we're also going to output like a bounding box of where in the image is this object located. So let's dive a little bit into what it might look like to actually build this as an inference service. So first, we'll probably have to download the image, fetch it from some kind of storage like Amazon S3. And then we might do some basic pre-processing. So maybe crop the image to the right size or apply some basic filters or transforms. And then when we actually want to do the object classification, we may have multiple different types of models. Right? This might depend on the user that you're using. You might be doing an A/B test, or you might use any number of other factors to decide which machine learning model you actually want to pass this through. In parallel, we also want to do object detection or image detection in order to find the bounding box that will return as part of the API. And then finally, we need to stitch all of this together into some kind of structured output format in order to return the information that we want from the API. So this is very clearly not just a single scikit-learn model or something like that. To build this kind of like end-to-end API, you end up having to stitch a lot of different machine learning and just business logic together. So now let's imagine that we want to actually deploy this as an online service, right? We want to have an API that we can query in real time with an image and get this response. So this comes with a lot of pretty strict requirements. So obviously, we want to minimize latency, because that directly impacts the user experience or maybe downstream systems. And we want to maximize throughput so that we can save cost, especially when machine learning models are very cost intensive. Along the same vein, we may also want to allocate fractional, like fine-grained resources. We may want multiple models to run on the same CPU or on the same GPU in order to save cost. And it's really important that we have a programmatic API to make sure that the data scientists or machine learning engineers that are building this application are able to be really productive when building, developing, and testing their application. And finally, when we do go to production, we need to have a rock-solid story, right? We need to have monitoring, we need to have solid upgrades, we need to have high availability, and these things are just table stakes. So note that a lot of these things are not really that related to machine learning, right? This isn't like directly tied to your model architecture. It's really about the infrastructure and the compute layer, and that's what RayServe is built to give you. So let's look at what is often kind of the naive solution to this, which is let's just take all of our models and all of our business logic and pack it up in a single container. So you might take multiple models, maybe from different libraries, even like PyTorch or TensorFlow. Write a little bit of Python logic to glue them together, put it behind a web server like FastAPI or Flask, and then package that all up into a container and deploy it on something like Kubernetes. I'm sure many of the people in this room have built or seen something like this in the past. And this is a really good way to get off the ground, right? This looks very similar to just deploying a normal web app or web server. But you're pretty quickly going to run into problems, right? Because you can't scale these models independently, and because machine learning models are often memory and compute intensive, this causes big problems. You end up with high latency, low throughput, and it's also very expensive, especially when you have many different models and they aren't all used for every invocation. So a more complex solution that addresses the problems in the basic kind of monolithic solution is to split up our models and treat them more like microservices, right? So imagine this architecture where we're still running on Kubernetes, but now instead of having just one container that's replicated, maybe we split each part of our application into its own kind of service. So here we have maybe a TensorFlow model that has 3 containers and a PyTorch model that has 2. And once again, we're using something like FastAPI to orchestrate everything and stitch it all together. So this solves our problem, right? Because now we can leverage Kubernetes, we can scale these things independently, we get a lot of power from this architecture. But this is really complicated, right? Every single one of these boxes is a new component that you have to maintain. And especially if you have data scientists and ML engineers who are trying to build and deploy like their end-to-end applications, this is a huge burden to put on them. It also makes local development and testing much, much harder. So today I'm going to tell you how RayServe offers a better solution for these types of multi-model inference applications. So with Serve, you can write a single Python program. You can still use your favorite tools and libraries and your favorite machine learning libraries like PyTorch and TensorFlow. And then you can seamlessly scale up across a cluster of CPUs and GPUs to build a high-performance and efficient inference API. So let's revisit the example that we had for content understanding and just imagine what it might look like as a Serve application. So we may still want to run on Kubernetes, like many of our users do, but now we have pods that are managed by RayServe. Our entire application is expressed as a single Python program, and it can be flexibly deployed across our Ray cluster that's running RayServe. We can allocate resources in a very flexible way, so we might have some of our nodes that have a GPU and CPUs like the top one, and some of them may only have CPUs. And we can also have the same kind of flexible resource allocation for each individual model. So in this case, maybe our image classifiers require 1/3 of a GPU and a CPU, where the object detector only requires a CPU. And the key here is that this entire picture is a single Python program. You can develop it and test it locally using your local IDE and just running it on your laptop. And when it's time to deploy it to production, you can deploy it and update it as just a single application, but still get all the benefits of running on a cluster and having all the power of the flexible resource allocation and a high-performance API. So with Ray 2.0, our goal is really simple. We want to make it as easy as possible to put these types of scalable machine learning applications into production. So the first goal here is we want to have a really great user experience for doing flexible model composition and building end-to-end online inference APIs instead of requiring handwriting a YAML file or stitching together many different microservices or something like that. We also want to make sure to improve efficiency and save costs, and we do that by adding advanced autoscaling functionality. And then finally, we've been really, really focused on production hardening and making sure that RayServe is rock solid in production, and especially on Kubernetes, as we see more and more of our users are moving towards Kubernetes. So let's dive into the first point here, which is the RayServe Model Composition API. So I talked a little bit about this in the intro, but the requirements for a model composition API, as we see it, are first of all, we want to be flexible. I think machine learning is very much an emerging domain, and we see a lot of different frameworks, different types of models, and oftentimes a lot of custom business logic required to stitch everything together. We want to make sure to satisfy all of that. We also think it's absolutely crucial that you can develop, test, and debug your applications locally. And finally, and maybe obviously, you have to be scalable and you have to be efficient when it's time to run in production. So our solution is the Model Composition API, which we've put a lot of work into with the Ray 2.0 release. So we've created this API to build graphs, which is just multiple models that can be stitched together with custom logic, of served deployments, which is an existing concept of each individual model in an application. You can still use the full flexibility of RayServe, so the fine-grained resource allocation and all of the functionality to make your application efficient. So you can author, configure, and scale each model independently. And then you can orchestrate the computation and stitch together the models just using regular Python code. You don't have to worry about like gRPC protocol or setting up ingresses or setting up Kubernetes services or anything like that. It's just a normal method call. So let's dive into a couple of the patterns that we see for model composition and how we can solve them with this API. So the first one is quite simple. Imagine that you just have multiple models that you want to chain together. So you have some kind of input. You want to pass that to a first model, and then take the output and pass it to a second. This is really easy to express in the API. So we're basically just going to use this bind call to define each one of our models. So here we're defining M1 and M2, which maybe they have different URIs for MLflow, or the model is saved in S3 or something like that. And then we just write a block of ordinary Python code that defines the orchestration logic. So here we take the input, we pass it to M1, we take the output of M1, and we pass it to M2. And that's all there is to it. So you can extend this to also implement something like ensembling, where you want to broadcast the input to multiple models and then combine it, maybe also using custom business logic. So in this case, we initialize the models in just the same way. But instead of chaining the output of M1 into M2, instead we just feed the input into both of them, and then we pass the output of both of them into a custom combine function. And note that this function, and it could also be a class, is just ordinary Python code. You can do anything you want inside of it. You could use another library. You could just write some business logic with if and else statements, anything you want in a normal Python function. And finally, one of the patterns that we're really excited about, because we've heard it a lot from our users, is this idea of dynamic selection. So sometimes based on the input or based on other parameters, like what user sent the request, you actually want to select a different model to handle the request. Because RayServe lets you just use ordinary Python code in order to write each node in this graph, this is also really easy to express. So here we're creating M1 and M2 like we did earlier, but we're also passing those into another node, which we're calling the selector. And this selector is going to, at runtime, take the input and decide which one of those it wants to pass, which one of those it wants to call, based on the input or based on the user ID or anything like that. And then you just get the output from the selector. So if we revisit this, this working example we had before of the content understanding application, you can see that in this example, we actually use all three of these patterns. So we chain the downloader and the preprocessor. We then do ensemble to do both classification and image detection. And we're also doing dynamic selection within the classifiers. And we can do this just by composing these really simple primitives that I showed you in the past couple of slides. And this is really expressive. It allows you to create all sorts of really complex topologies and do it with really simple code. So to summarize, the model composition API lets you write your models as ordinary classes. And then you can flexibly compose the models and business logic just using Python code. You can run, test, and debug the entire end-to-end application on your laptop. And then when you deploy to production, you can configure and scale all of these models independently across a cluster. So speaking of scaling, let's dive into the second highlight for Ray 2.0, which is autoscaling. So obviously, one of the key requirements for serving machine learning models in production is to reduce cost, right? Machine learning models are very compute intensive, and running GPUs and CPUs 24/7 really adds up very quickly. So in addition, we have some other requirements. You know, many times, not all of the models are used at all times. You might have a periodic cycle throughout the day, or you might have just different traffic patterns from users that are variable throughout the day. It can also be really hard to tune hardware utilization targets, which is what a lot of autoscaling algorithms are based on. This might require profiling your code, really understanding low-level details, or even like rewriting your models to get them to work with hardware utilization-based approaches. And finally, it's also really crucial that autoscaling works with multi-model or model composition applications like the ones that I just described. So our solution is to add advanced autoscaling features to RayServe. So this supports scaling down to 0, which means that you can have models that are not occupying any resources until requests come in for that specific model. It uses request queue lengths instead of hardware utilization, which means you don't have to do any profiling or rewriting your code at all. And it pretty much just works out of the box. And it's also fully compatible with the model composition API that I just got done explaining, which means that you can independently autoscale each model in your end-to-end application. So let's see how this might work for the example that I've been using throughout the talk. So let's focus in on this image classifier. So you can imagine that maybe based on the user request pattern, we're sending a lot more images to classifier number 1. So in this case, classifier number 1 is overloaded. There's a long queue built up, which means latency is high, and response times are long. So in this case, RayServe would see that the queue size for the classifier number 1 is obviously much longer than the target. We want to keep these queues short so that we can keep response times down. Oops, I went one slide too much. So in this case, we might add more replicas, and this would happen completely automatically. So now we have 4 replicas of image classifier number 1, and the load is balanced across the replicas. At the same time, notice that image classifier number 3 hasn't been used. So after some idle timeout, we would also scale this classifier number 3 down, and at this point, we have 0 replicas of that model. This wouldn't get scaled up until we actually have a request to use that model, which is really important for applications that have very sparse invocation patterns. And the key here is this is really easy to get started. All you have to do is set up a few basic parameters. You don't have to set up a metrics ingest stack. You don't have to profile your code. And you don't have to change your models or anything like that. And we also support scale to 0, and it integrates fully with model composition. So you can see a sample of an autoscaling config at the bottom. OK, so let's dive into the third highlight, which is our efforts around production hardening. So obviously, putting machine learning models into production means you have to solve some really serious operational problems that aren't related to machine learning. So you need to handle updating your code and your models without downtime. As you scale up, failures get more likely, and you need to be able to handle them gracefully. And you also need really good monitoring, observability, and alerting for when things do go wrong. So our goal that we've been working towards is really to try to get the best of both worlds and get the flexibility, the user experience, and the efficiency of RayServe, but also provide the operational benefits of a system like Kubernetes. So of course, RayServe has continued to be supported on other stacks, but we're really doubling down and trying to make it integrate as well as we can with Kubernetes. So our first major effort has been around building a dedicated operator for RayServe into KubeRay, which you may have heard about at other talks today. So let's look at an example of this. So imagine that you have your Python application running on your laptop. So you might do the development loop here on the left. And then when you're ready to deploy, you'd use this new command, serve build. What serve build does is takes your application and basically just transforms it into a structured format that can be embedded inside of a Kubernetes manifest. This is really important because it means now we can apply that manifest directly to the cluster. So we can deploy, upgrade, and monitor our RayServe application using standard Kubernetes tooling, just using kubectl. So what's actually happening over here is we have a Ray service operator, like I said, that's part of KubeRay, that will read this manifest, and it'll make changes in the cluster to create Ray clusters, deploy your serve application to them, and then also handle updates and monitoring over time. And this comes with really crucial features like zero downtime updates. It will automatically health check and recover from failures. And like I said earlier, it also integrates really cleanly with other Kubernetes tooling and makes it really easy to build, for example, CI/CD or automation workflows with RayServe. So another effort in order to improve production hardening has been GCS fault tolerance. So this has been a huge effort jointly between the RayServe and the Ray core team. If you're not intimately familiar with the Ray architecture, prior to Ray 2.0, it had a single point of failure. So on the Ray head node, we had this process called the GCS, which is essentially like the global coordinator for the cluster. It handles scheduling and health checking actors and things like that. And if this were to fail, which is unlikely because there's only a single copy of it, but may happen over time, if this were to fail or the head node were to fail, it would take down the entire cluster. So of course, you could replicate the cluster and have multiple copies, or you could work around it by health checking the cluster and restarting it when this did happen. Obviously, this is not a good situation for running a production online inference API. So in Ray 2.0, we're really excited to announce that we put in a ton of work and made it so that Ray can recover from GCS failures. So if the GCS fails, you can actually still continue to run critical functions like tasks and actors will continue to run uninterrupted. And when running on Kubernetes, a new GCS will automatically be started, and the cluster will recover to a completely operational state. And the really important part here is that we put in a lot of work to make it so that Ray serve applications will continue to serve traffic without any disruption during this GCS downtime. And to show that this really works, we've actually been doing a lot of chaos testing. So basically what we do is we run a sample Ray serve application. Every minute, we randomly kill a node in the cluster. So obviously, this is a really stressful example. I would hope that this doesn't happen in your production cluster. And at the same time, we're running a load test. So here on the top, you can see the success versus failure rate. And you can see that even though we're killing nodes repeatedly as this benchmark is running, we're able to maintain more than 99.99% uptime. And by the way, killing nodes also includes the head node. So if we were to run this prior to Ray 2.0 and prior to making all these fixes, you would see periods of downtime anytime that the head node went down. So we're super excited about this feature. This has been a long-standing request, and we really think it's going to reduce the operational burden for a lot of our users. So to summarize the state of RayServe in 2.0. So our goal, we want to make it as easy as possible to put scalable machine learning applications into production. So we've doubled down and really tried to improve our user experience for doing model composition. We've also added advanced autoscaling features to help you save cost and reduce resources. And we've put a huge amount of work into production hardening with an increased focus on making it really easy to deploy, update, and manage your applications on Kubernetes. So we have a number of other talks at the summit, some of which happened earlier today, that are deep dives into some of the topics that I talked about here. So Shreyas will be talking about operationalizing RayServe on Kubernetes tomorrow. And if you didn't have a chance to catch the first two, they'll be available. The recordings will be available after the summit. We also had two talks from the community about how they've used RayServe, and these will also be available after the summit. So that's the end of the talk. Thank you, and I'm happy to take questions. Oh, sorry. If you're going to ask a question, can you just keep your hand raised, and Thomas will bring you a microphone. Go ahead.
If you're scaling up from 0, what's the cold start time for the underlying compute to warm up?
Yeah, so that's a very complicated question because it depends on a lot of factors. If you already have the compute and the model is sitting in the object store, it could be well under a second. And actually, Fred, the community talk that I had about the zero-copy model loading, he talked a lot about how to optimize this cold start time. If you've scaled down and you have to provision a node from your cloud provider, it could take much longer. So it depends a little bit on your setup. But optimizing this has been a consistent feature request, and that's something that we plan to work on going forward. In the back.
Hi. My question is around autoscaling. So you mentioned that the queue length is used as a heuristic to make scaling decisions. Is this customizable in the sense that queue lengths may not always be very informative in terms of like how inputs may vary? Like a large queue may not always need scaling up, whereas like a shorter queue length may need something. So I'm just wondering if that's customizable.
Yeah. So it is very customizable. So our goal was to really make it so that, make simple things simple. So make it so that most applications work without any customization. But we do have a range of parameters that you can tune for different situations. And yeah, I encourage you to check out the documentation. We have a page that details all of the parameters. There's one in the middle here.
Hi. So on the same subject of autoscaling, is it dependent on Kubernetes doing the autoscaling, or has its own logic that supersedes, or how does it interact in Kubernetes?
Yeah. So the autoscaler that I talked about here is at the RayServe level. So it'll change, it'll adjust the number of replicas that you have for a given model. That relies on an underlying cluster level autoscaler to actually provision nodes that satisfy that request. That is fully featured inside of Ray and inside of kubeRay, the operator. So yeah, there are a few layers here, but yeah, kubeRay and RayServe plus kubeRay provides the full functionality. Yeah, they're independently configured. You could use one without you could use the kubeRay autoscaler without serve, but not vice versa. On the right over here, yeah.
Hey, on the first slide, I saw that you had some integrations with different data apps, like Gradio or Streamlit. I was wondering, what does that process actually look like to develop a data app on top of the models that you build here?
Yeah, so we've actually been working, we have a project right now, collaboration with the Gradio team, to make it so that you can really easily take two things. One, you can take a Gradio application and you can just put it on top of RayServe and just scale it up. So if you had a multi-model Gradio application, it will, you can increase the throughput, reduce the latency. And that should basically be a drag and drop, no changes. We're also trying to make it so that you can use Gradio as a UI for an existing Ray Serve application. So both of those are kind of in the works, like experimental stage. But we do have documentation for them, and I would encourage you to check it out and file an issue if you have feedback. Yeah, in the front left. Getting Thomas's exercise today.
At the end of the day, right? So what about the EKS? Sorry, the overall Kubernetes, is it going to be the de facto for Ray, or you are developing your own kind of a much optimized auto-scaling?
Yeah, so this is kind of a bigger question than Ray Serve, but in general, we are like basically doubling down on Kubernetes. We see a huge portion of our users that are currently on Kubernetes or have plans to move to it. So same as I said in the talk, like we're going to continue to support other stacks because we can't only work on Kubernetes, but we want to make it as seamless as possible, and we don't plan to build like our own like Kubernetes competitor cluster management layer or something like that.
Is that a requirement, or you can have just a
Kubernetes is not a requirement,
okay.
no. So Ray has a built-in cluster launcher that works with a bunch of different backends. You can use EC2 instances, you can use Google VMs, you can also use Azure. And a lot of those are community contributed and maintained, and if you have a backend that isn't supported, then we'd love to work with you to get it working. Okay, I think that's all the questions. Thank you so much.